Swayam Prabha. Digital India. Educated India.
So, let us begin the lecture today, and what I'll do is basically talk a little bit about things which you have already known, but again try to put them in a kind of a formal context. Okay. We were looking at matrices and we defined the adjoint operator. Now, I want to talk about some of the properties of these operators, okay, matrix as an operator, and basically I want to talk about eigenvalues and eigenvectors. Okay. So, what is the definition of an eigenvalue? An eigenvalue is lambda and u is an eigenvector. So, lambda is an eigenvalue, u is the eigenvector if it satisfies this equation. Now, by definition an eigenvector has to be a non-zero vector, because if u is 0 it automatically satisfies a 0 0 lambda multiplied by 0 0. Okay. So, an eigenvector has to be a non-zero vector. So, if you are finding eigenvectors and you find that 0 as the eigenvector, then clearly you done something wrong. Okay. 0 can never be but 0 can be an eigenvalue, okay, but the eigenvector has to be non-zero. Eigenvalue can be 0. Now, what is this property of the eigenvector? If you have an eigenvector and if your matrix, if your operator is operating on the eigenvector, you get the same vector with a different magnitude. It is just lambda times the original vector. Okay. The direction is not changing. If it is not an eigenvector, if you multiply by au, you will get another vector v which may be different from this. So, just a scalar multiple. Okay. So, when an operator acts on an eigenvector, okay, we get a different we get a vector in the same direction. Well, when I say same direction, if lambda is negative, it will be opposite direction. Okay. So, in the same direction as the eigenvector. So, same or opposite, same slash opposite. Okay. The direction of the vector does not change to something which is at an angle. Is, let us say, collinear. Operation. Okay. So, and if lambda is positive, then the direction is the same. If lambda is negative, direction is reversed, but the magnitude is going to change. The magnitude is going to be decided by lambda. Okay, the magnitude of the eigenvector changes by so basically if I have a vector u, I just operate on it by A. That means I do a matrix multiplication. I will get another vector which is going to be lambda times u. Okay, lambda is now represents the magnitude. You had some magnitude originally. The new vector has the collinear with u. Collinear means either in the same direction or opposite direction, and the magnitude of this will be mod lambda times that. Okay, magnitude means you can look at it as norm. Okay, when I say magnitude, I mean norm. So that is the geometric interpretation of eigenvalue and eigenvector. Okay. What I will do is talk about some properties of eigenvalues and eigenvectors, which we will use later on. Okay. So let us say I can call it theorem 1, eigenvalues of A and of A star are the same, are identical. That is, whatever A is the original matrix given to you. Okay, A star is the adjoint which you find by looking at the transpose. So if you have given a matrix A and if you have calculated the eigenvalues of A, you do not have to go back and calculate the eigenvalues of A transpose, they are the same. That is what I am trying to say. Okay. And most of the things that I am going to talk about proofs are quite straightforward. So now we have AU equals lambda u. This is the eigenvalue of the matrix A. So, and remember, whenever we are talking about eigenvalues, A is going to be a square matrix. Okay, you cannot find eigenvalues for a rectangular matrix where m is not equal to n. So, A by definition let us say n by n. So now AU equals lambda u, A is the operator, this is the definition, I have just written down the definition. Okay. So basically if you find a vector u for which you find a lambda for which this has a non-zero solution, the non-zero solution is the eigenvector. Okay. So similarly for A star of u eta u. Okay. So basically eta is the eigenvalues of A star and lambda is eigenvalue of A. Okay. Now we can rewrite these equations by doing some small transformation here as A minus lambda I u equals 0 and A star minus lambda minus eta I u equal to 0. Now maybe it is confusing if I use the same u here, because eigenvectors are likely to be different. So, let me write this as V, man. Maybe you can make that change, because eigenvectors will be different. So, I do not want to confuse you by saying if I use the same symbol, you may think it is the same vector. Okay. So, I am going to write this as V. What have I done? Because lambda is just multiplying, is a scalar, and it is just going to the lambda u1 first coordinate will come. So, it will only affect the diagonal. So, basically when I shift it here, only the diagonal elements are going to change. Now, by definition, u and v have to be non-zero, okay. And when can I get a non-zero solution? Only if the determinant of this matrix is 0, okay. To get a non-zero u and v, we must have determinant of A minus lambda I equal to 0 and determinant of A star minus eta I equal to 0. Only then I can get a non-zero solution, because basically what does this determinant equal to 0 imply? It implies that what I was talking about earlier, that these columns and rows of this matrix A minus lambda I are dependent, okay. Basically this implies there is a dependency of the rows and columns of A minus lambda I. I mean that is the reason I am getting a non-zero solution, otherwise I will get only the 0 solution, okay. So, basically all these concepts are connected. I mean you were calculating eigenvalues by putting determinant equal to 0, determinant equal to 0 gives you a non-zero solution, the same as those constants Ci's that we were talking about. So, non-zero solution implies that the determinant is 0, it also implies that these rows and columns are dependent on each other. So, now we also know that the determinant of a matrix is equal to the determinant of its transpose, okay. So, if the determinant of this is 0, that means the determinant of the transpose is 0. This implies determinant of A minus lambda I transpose is 0, or determinant of A transpose minus lambda I is 0. And you also know that A adjoint for matrix is nothing but the transpose. So, this tells you A star equals A transpose, okay. So, basically both of these are identical. When you solve for this determinant equal to 0, you will get an nth order polynomial, okay. So, basically the roots of lambda and the roots of eta, hence lambda and eta are roots of the same nth order polynomial and are identical, okay. The eigenvalues are identical, the eigenvectors are I am not talking about. So, if we have some doubts about why is determinant of B equal to determinant of B transpose, one simple way is for you to actually take an example and do it and verify, okay. No, that is not a formal proof, but these are very standard concepts in linear algebra which you can read. I am not going to bother. because my objective is something else. Okay. So, I mean some of these things which I am saying you doubt, then go and read a book and figure it out and understand it better. The other thing I want to, the next theorem is the eigenvalues of a self-adjoint matrix are real, because eigenvalues are given by roots of a polynomial. The roots of a polynomial can be complex conjugate, right, you can get complex numbers, but if your eigenvalues are of a matrix which is self-adjoint. What do I mean by self-adjoint? For matrix it is real symmetric matrix. Okay. So, your matrix is real symmetric, the eigenvalues are going to be real, you cannot get complex eigenvalues. Okay. This means symmetric matrix has only real eigenvalues. I am assuming that all the elements of A are real. Okay. A has only real and because we are all engineers and we are doing modeling of real systems, all these elements will be real. You won't get imaginary numbers, all your properties are real, all the physical quantities are real. So, we are dealing with real numbers, we are not dealing with imaginary variables. Okay. So, that is not a real big assumption. So, although the eigenvalues are roots of an nth order polynomial, all the roots will be real, that is what I am saying. Okay. So, this means all the roots, all the n roots no complex conjugates. So, let us consider AU equals lambda u. This is the eigenvalue problem. So, this problem I will call this an eigenvalue problem. Eigenvalue problem means I am finding the eigenvalues and the eigenvectors. And what I am going to do is I am going to take the inner product of this on both sides with u. Okay. What I want to do? Yeah, I want to prove it is real. So, take inner product of this on both sides with u. So, inner product of u with AU equals inner product of u with lambda u. So, I am taking the inner product on the left with u, that means the left is u and the right is whatever is there. Okay. I mean you can take the inner product in any which way you want, you can take inner product AU with u also. Okay. But right now I am doing this, if you do it the other way also you will get the same result that I am doing. So, this is I am going to call it inner product on the left with u, that means inner product of u with AU and u with lambda u. So, this is inner product on the left, okay, means the u is on the left. what is this? By definition of adjoint, this can be written as inner product of A star u with u, and the right hand side I will keep it as it is, inner product of u with lambda u. What have I done? This is the definition of the adjoint. The way I defined the adjoint was inner product of u a u is equal to A star u with u. This is by definition of okay, and I am talking about a self adjoint operator, which means A star, the adjoint is equal to itself. So, A star will be equal to A, okay, A star is A transpose is equal to A. So, this I am going to write as because okay, and what is AU? AU is again lambda u. This implies now I can't assume my eigenvalues are real. Why? Because I am trying to prove that my eigenvalues are real. So, I have to allow for the fact that my eigenvalues can be complex, conjugate, right. So, because I am, so remember lambdas can be complex since they are roots of a polynomial. And so, I have to work in the complex inner product space. What is this complex inner product space? You conjugate the first guy. So, when I am conjugating the first guy, when I take the lambda out, I will get lambda bar. When I take the lambda out here, I get only lambda, because I am not conjugating this. So, this is lambda bar u with u equals lambda of okay. When the right hand side, when I take it out, I get only lambda, left hand side I get lambda bar, and this is lambda bar minus lambda and basically by definition the eigenvector u is non-zero, therefore, the inner product of u with u will be non-zero. The only way this can be satisfied is this lambda is equal to lambda bar, which means lambda is real. This inner product of u with u is not equal to 0, as u is not equal to 0, therefore, lambda equals lambda bar and lambda is real. So, whatever we have done in the past, I mean what is the norm, what is an inner product, what is all of this small subtle points that I was trying to explain earlier are being used here. Inner product of u with itself is non-zero for a non-zero u, that is one of the axioms we had, okay. That is being used, and only way this can be satisfied is if lambda equal to lambda bar, therefore, the eigenvalues are real, okay. So, this is so when we are doing, again just to tell you why are we doing all this, when we talk about differential equations, again we will talk about self adjoint. There again we will see that if the operator is self adjoint, the eigenvalues are real. So, that is the connection I am trying to make, okay. So, whatever if you do not think of this as a self adjoint and what the properties are, this extension to other areas will be difficult or will be difficult for you to understand and see. And the thing I want to do, the next point I want to make here is vectors of a real symmetric matrix form an orthogonal set. So, what this means is you have found out the eigenvalues by, and we are talking about real symmetric matrix, we are talking about a self adjoint operator. You found the eigenvalues by finding the roots of the polynomial, by substituting the lambdas and solving AU equals lambda u, you have found the eigenvectors. Okay? And now, you supposing you have a 3 by 3 matrix, you will have a cubic polynomial, have 3 eigenvectors, and we are talking about real symmetric matrix, you will have 3 eigenvectors, 3 eigenvalues, 3 eigenvectors. What I am saying is these 3 eigenvectors that you are going to get are going to be perpendicular to each other. First one is perpendicular to second and third, second is going to be perpendicular to third, etc., etc. Okay, every vector is perpendicular to every other vector. Okay. So, I. So, basically now I am talking as the subscript I and the superscript I represents the ith vector, lambda subscript I tells you the ith eigenvalue. Okay. Because the scalar I am putting subscript I here, vector I put a superscript, and I have a uj equals lambda uj lambda j uj. So, the 2 different eigenvalues I am looking at. So, the 2 eigenvalues are distinct, they are different. Okay. The eigenvalue vector of the 2 will be perpendicular, that is what we want to show. So, I have a ui equals lambda I ui for ith eigenvalue, and basically I is lambda I is not equal to lambda j, because I look at 2 different eigenvectors, I can look at the same eigenvector and say it is perpendicular to each other. So, when I am considering, I have to make sure that these eigenvalues are distinct. Okay. So, basically lambda is not equal to lambda j. Again the methodology is the same. See, you are going to only do inner products in this course. So, better get comfortable with doing inner products. Okay. We are going to do inner products again. I will take the inner product of this with uj, of this with ui. Okay. So, let me keep my life simple. I will take inner product of uj on the left and of this with ui, but I am going to do this on the right. So, this is what I call inner product on the left. Okay. I am taking the uj on the left in both the terms. Here I am taking inner product with ui, because you will see why I am doing this, because it is easy for you when the next step comes. Okay. Now, you remember that we are going to look at real symmetric matrix self adjoint thing, that is something we are talking about. Now, this can be written as A star uj with ui by definition of adjoint. So, this is, let us say this is equation 1, this is equation 2. So, equation 1 becomes A star uj with ui, and what I will do is, we have already shown that the eigenvalues are real. If the eigenvalues are real, the eigenvectors will also be real, because you only have real coefficients. Okay, when you are solving a system of linear equations, you get only real. So now we are only talking about real. So I am going to take this guy out, and I am going to write this as lambda I, inner product of uj with ui. Okay, and this is nothing but, because it is self adjoint, A star equals A. This is by definition of A star. In the first equation, by definition of A star, it comes here, because it is self adjoint. I get A uj ui equals and this guy at the bottom is this equation 2. Now, when I take the lambda j out here, I do not have to put a complex conjugate, because everything is real, because I am talking about self adjoint, and because I have already shown eigenvalues are real. Okay, I will just pull the lambda j out. Okay, now subtract these two. What do I get? Left hand side will be 0. So now you see the advantage of doing one inner product on the left and one inner product on the right. Otherwise, I would have gotten the thing reversed. So now I have it on the same side. So I get 0 here equals lambda I minus lambda j times inner product of uj with ui. Okay. So basically, we are looking at the situation where the lambda I and the lambda j are distinct, they are different from each other, they are not the same. So lambda I minus lambda j cannot be 0. Okay. So lambda I minus lambda j is not equal to 0, as they are distinct from each other. Therefore, inner product of uj with ui is equal to 0. That is the only way this can be satisfied. Okay. So now, just to give you the background, I mean, you saw that there was an advantage of using orthogonal vectors as a basis for solving, for writing one vector as a linear combination. You could find the coefficients very easily. So basically, our strategy is going to be to use these eigenvectors as a basis set, because they form an orthogonal set. Every problem you have a different A matrix. Okay, you take some other problem, you can write it in the form of a matrix. A will be different, but you try to express the solution. So the question is, so we can use this eigenvector set as a basis to represent an vector. Okay. And that is what I said, because that is something which is occurring naturally to that problem. If I have another problem, I have another A. Of course, what I have talked about is kind of limited in the sense that it is valid only for real symmetric matrices. Whatever I have done today is only for real symmetric matrix. So we will see how to extend this to the case when A is not real symmetric. Okay, it's possible. So first of all, okay, so this is clearly possible for A equals A transpose, because whatever I have done so far, all these theorems are only for A equals A transpose. How to extend when A is not equal to A transpose? That is something which we will do. Okay. But before we go to next class, which is tomorrow, I want to just summarize a couple of things. The eigenvectors are only determined to within a scalar multiple. What do I mean by that? I am saying if let us say 2 3 is an eigenvector, 4 6 is also an eigenvector. Eigenvectors are not going to be determined uniquely. When you are trying to find eigenvectors, you will find that the number of equations will be less than, number of independent equations will be less than the number of unknowns. Okay. So, you will put some value for one of the variables and find the other variables. Since you can put any value, you can get different eigenvectors. Okay. So, you can see that, I mean, if you have an equation of the form, actually stupid, okay, 2 and 3, let us stick to 2 and 3. Okay. So, that is something you have to keep in mind. And you can always make it unique by making the norm 1. Okay. So, basically this will have a different length, that will have a different length, 2 3 and 4 6. 2 3 is one eigenvector, let us say 4 6 is another eigenvector, and if you normalize it, what would you get? Square root of 4 plus 9 13, right, 1 by root 13 2 3, and this will be square root of 1 by 52, square root of 52, 4 6. I am looking at the 2 norm, okay, using the definition of the 2 norm. So, what have I done? I have just divided by the length, the square root of a square plus b squared, and you see they are identical. So, now if I were to normalize the eigenvectors and I make my set, I will get an orthonormal set. Okay. So, basically point is the eigenvectors are not going to be determined uniquely. You can get one vector, you can multiply that vector by 4 and you can say that is my eigenvector. Somebody can multiply by 20, that is also an eigenvector. But if you want to have a common basis, then you make the length equal to 1, then the answer is unique. Okay. So, you can see the square root of 4 comes out, 2 comes out, you will get the same thing. This is equal to 1 by root 13, 2 and 3. Okay. So, we can normalize the eigenvectors to have unit norm. Okay. So, basically if I do the normalization, then u1, u2, un, the set will be such that inner product of ui with uj equals delta ij, if you do the normalization. So, I want you to think about what we have done and understand these things, because tomorrow when you solve problems you will realize that you get you can't get 0 as an eigenvector. If you get 0 as an eigenvector, then your eigenvalue is wrong or your eigenvector calculation is wrong. And if it is real symmetric, we will see you have to have real eigenvalues and the eigenvectors have to be perpendicular. If the eigenvectors are not perpendicular, then you have a problem, okay, because I have proven formally. What we will do is find out and explain that these perpendicular eigenvectors can form an independent set, therefore, they can be used as a basis. We will extend this to non self adjoint operators tomorrow, so that you are not restricted to this. Then once you do that, then we can do other things. Thank you.